Up until this point, we've been dealing with chemical reactions at equilibrium. What if our chemical reaction is not at equilibrium? How will we know? Well, one way that we can check is by calculating something called the reaction quotient. We compare this answer to the equilibrium constant, and it tells us if we are at equilibrium or not. Now you may notice that our reaction quotient looks very similar to our equilibrium constant, and that is on purpose. And we set it up in the exact same way with products raised to the coefficients divided by reactants raised to the coefficients. We then can compare the Q value, which is our reaction quotient, to our equilibrium constant to determine if we are at equilibrium. If Q is larger than K, if it's greater, that means that we have more products than reactants, and so our reaction is going to proceed toward the reactants until we reach equilibrium. So if Q is larger, we're going to run the reaction in the reverse direction towards the reactants. And we're in this portion of the graph here where Q is larger than K. And the reaction proceeds in the reverse direction until we reach equilibrium. When K is larger than Q, we're going to proceed in the forward direction. We're going to move towards the production of more products because we will have an excess of reactants. The denominator is going to be larger. So we're going to increase the amount of products by moving the reaction in the forward direction. When Q is equal to K, that means that our chemical reaction is at equilibrium. It's not going to proceed in the forward direction or the reverse direction. The products and reactants, overall, their concentration will not change. We do have a couple of other cases when we have just reactants and no products. That means that our Q is going to be 0, and our reaction is going to need to proceed in the forward direction to reach equilibrium. If we have just products and no reactants, then Q is going to be infinity, and it'll have to proceed in the reverse direction to produce the reactants. Let's try an example. For the following reaction, determine which direction our reaction is going to proceed. And in order to do that, we need to find Q, our reaction quotient. Because we're given pressures, it is going to be QP. So we're going to take the pressure of the products divided by the pressures of the reactants. We can substitute in the pressures that we were given. And we can calculate what our Q value is. So our QP is equal to 10.8. We're going to compare that to the KP for the chemical reaction, which is 81. And so our Q, which is the 10.8, is smaller than the K, which is 81.9. And so that means that our reaction is going to proceed to the right to form more products. So we're going to produce more products in this chemical reaction. Here's a practice for you. Pause the video and see whether or not each of these experiments are at equilibrium. The Q is going to be products over reactants. We can substitute in for each one of our experiments. So let's start with experiment 1. Substitute in the values. So for CS, H2, remember that's to the 4th power, our methane, and our H2S, and that is going to be squared. And so if we calculate, we get 1.24. Our Kc is 3.59, and so the K value is larger, and so it's going to proceed in the forward direction. So we're going to move towards the products. If we look at experiment 2 and use the values for experiment 2, remember to raise to the 4th power for our hydrogen. And squared for our dihydrogen monosulfide, we find that the value is 5.86. Okay, this is larger than our Kc value, which means the reaction is going to proceed backwards or in the reverse direction. If we look at experiment 3, and substitute in our values, we square that. Our experiment 3 is equal to 3.59, which is our Kc, so we are at equilibrium. Here's another practice for you to determine what the equilibrium concentration of PCl5 is. Pause the video and determine the concentration. If we're trying to find the equilibrium concentration, we're going to set up our equilibrium constant is equal to products over reactants. Because we're given the amount in moles for the PCl3 and the Cl2, we can determine their concentration by taking the moles and dividing by the volume. Once we have that information, we can plug it into our equation, but let's first rearrange it. So PCl5 is what we're trying to find. Let's get that isolated by multiplying both sides by PCl5 and then dividing by our equilibrium constant. So now if we want to find our PCl5, we can substitute in our values. So if we take 0.203 divided by 0.5, we end up with a concentration of 0.406 molar for each of the reactants. We can divide by our equilibrium constant. And when we solve that, we find that, oops, not Kc, this is the PCl5 concentration, is equal to 2.60 molar at equilibrium.